Welcome to this session, which is going to be on natural hazards, which I'm going to cover tectonic, atmospheric, extreme weather in the UK, and climate change. And just to point out there that I've put this symbol on there to remind you, please do pause, play, rewind this clip. I will be going at quite a pace, so if there's something that you've missed, please do go back to it at a later time. Very quick reminder, the Geography GCSE has 3 papers. The physical geography paper covers natural hazards, it covers ecosystems, it covers coasts and rivers, and then the human geography paper covers urban world, economic world, resource management, and then finally the geographical applications paper, paper 3, includes that issue evaluation and our fieldwork that we've done, Barnsley and Mappleton. We will be going through those tectonic hazards now, atmospheric hazards and climate change. So to get started with tectonic hazards, what we're looking at today are the factors that affect the risk of a hazard. And the first of that is location. If you live near a tectonic plate boundary, the likelihood is you are going to experience either earthquakes or volcanoes simply due to your location. Also, population density. Take India, for example, which is very, very densely populated. Because it's densely populated, if there's an earthquake and buildings fall over, the likelihood is you're more likely to be crushed in that earthquake. Climate is the next one. If you live in, say, somewhere near the Sahara Desert, around 30 degrees north of the equator, you're more likely to experience drought due to that lack of water. And then finally, wealth as well. You can see the blue countries here are HICs. These have more money if there were to be a natural disaster to take care of themselves, whereas the poorer countries would be less likely to be able to take care of themselves and would experience more, the effects more severely. The 4 layers of the Earth then. The 4 layers of the Earth we know are called, the outer layer is called the crust. That is made of solid rock. The layer underneath that is called the mantle, and that is made of liquid rock. They are the most important 2 you need to be aware of. Underneath that, you have the outer core, and then you also have the inner core. What are convection currents then? If we go back to, if I just get my pen back, if we go back to the layers of the Earth, we know the outer layer of the Earth is called the crust, which is made of solid rock. Underneath that, we have the mantle, which is made of liquid rock, very, very hot indeed, up to 4,000 degrees Celsius. And with that hot rock underneath the Earth, underneath the crust, it rises and then it falls. It rises and then it falls. Notice the circular motion which I'm creating. With that rising and falling magma, that's going to create friction between the liquid rock and the solid rock about there. We also know that the crust isn't just one large piece. It is broken up into different plate tectonics as so. So when that liquid rock is rising and falling, the friction that is created between the thick liquid rock and the crust is actually moving these plates apart. These are called convection currents. You can see another diagram of the correct convection currents there, where the liquid rock is rising and falling underneath the crust of the Earth. What are the names of each plate boundary then? We know that we have our first plate here, which is called a constructive plate boundary, where the plates are actually moving apart from one another. That creates little friction. There's not a lot of friction there at all. So you do get earthquakes, but they are very, very gentle indeed. But you also get volcanic eruptions creating shield volcanoes, which I'll come to shortly. The next one is a conservative plate boundary. At a conservative plate boundary, we know that the plates are moving past one another, creating friction. In this example, this plate is actually moving fast, this plate is moving slow, which is creating friction along this fault line here. Another example might be that one plate is moving in this direction and another is moving in that direction. At this plate boundary, we know we get earthquakes, but don't get volcanoes. And finally then, this is a destructive plate boundary. We know that at a destructive plate boundary, the oceanic denser, that means heavier, the oceanic dense crust subducts, that means goes under, beneath the continental crust. That melts, forming a magma chamber. As pressure builds, it goes up the main vent, which I will come to shortly. Here we get earthquakes and we also get volcanoes. These volcanoes, though, are composite volcanoes. What happens at each plate's boundary then? I've just mentioned there, we know we get volcanoes at these two plate boundaries, but we get earthquakes at all three. However, the earthquakes at a constructive plate boundary are going to be less severe, whereas at a destructive and conservative boundary, they are going to be more severe. What are the differences then between a composite and a shield volcano? You can see here on the left-hand side, we have a shield volcano, which looks very, very wide indeed. And on the other side, we have a composite volcano there. Remind yourself if you need to go back to where these form, because a shield volcano forms at a constructive boundary. Quite often we get lots of these in Iceland, and these are formed at destructive plate boundaries. Now, a shield volcano is a very, very gentle eruption. There's not very much friction there, so the eruption is gentle and it sort of bubbles out, the lava does, whereas these ones can take years and years and years to erupt, and they are very, very violent, a composite volcano. You can also see the base of a shield volcano is very wide compared to a narrow base on a composite. These ones are very, very steep, where these ones are very, very gentle sloping. The features of a volcano then, underneath the volcano, we know we have this thing called a magma chamber, where the magma is stored, and as pressure builds, that magma will force itself up cracks and create a main vent through the crust of the earth. And eventually, that magma will come out of the top as lava. As soon as you can see magma, it's not magma anymore, it's called lava. That is when the magma is cooling down. So we have lava going down the side of a volcano, but as well coming out, we have rock or volcanic bombs, either or. And also in a violent eruption, we may get ash, gas, and dust that also is ejected from the crater. If there's loads and loads of pressure, sometimes you get a secondary cone and a secondary vent, cone and vent there, where additional pressure causes some magma to escape out of the side. And finally, these layers here, you can see, are layers of solidified lava and then hardened ash and dust, which have settled over thousands and thousands of years. So these are layers of ash and solidified lava, and over the thousands and thousands of years, that creates the composite volcanoes to become much, much bigger in size. Why on earth would you live near a volcano then? Three main reasons. Number one, tourism. Tourists like to visit here, and tourists, as a tour guide, may take you up the side of the volcano to see it, when it's not erupting, obviously. Fertile soils. The soil around the volcano are normally really, really rich in minerals, so farmers can plant crops and earn lots of money there, which will support the country with the tax, and then also geothermal energy. How do earthquakes actually happen then? Let's just take the example of a conservative plate boundary. If I quickly sketch a conservative plate boundary out here then, I've not done that very well, where this plate is moving in this direction and this plate is moving in this direction. Now it looks quite smooth here, but in reality, those sides there will be very, very uneven, and it will be causing lots of friction, a little bit like if you rub your knuckles past one another. But let's just focus on this side here. I'm going to re-sketch this and actually do it from the side on view. So if we imagine that we have one plate tectonic on the left hand side here and another plate tectonic on the right hand side here, and notice that they are touching just there. Imagine that this plate on the right, plate A, is actually going into the board, but plate B is coming towards your screen now. And these plate tectonics have caught one another there. This is called the focus. This is where pressure is now building as the plates rub past one another. Eventually those plates are going to slip, and seismic waves are going to be released, a little bit like sound waves. These are vibration waves called seismic waves. And the first point that they are going to reach the Earth's surface there is the epicenter. The epicenter is the point directly above the focus on the Earth's surface. So we've got the focus where the energy is released from. We have the seismic waves, which are the energy itself, and then the epicenter there at the very, very top. Some people think that that's all that an earthquake is, but we know that if the earthquake was even shallower in the crust, if the focus happened to be there where it got caught, actually the earthquake at the epicenter would be even stronger, because that may be only 2 miles deep, whereas this may be 30 miles deep. So that would influence the impact of an earthquake. There's a diagram there just to show you a little bit clearer what I mean by that. We there have the epicenter, the focus, sorry, there. We've got the epicenter, the point directly above the focus. You've got the seismic waves, and you also have this black line, which is the fault line, the line, the gap between the two plate tectonics. What is a primary effect? A primary effect happens during an earthquake, e.g. schools collapsing or pipes bursting. A secondary effect is things that happen after the earthquake or as a result of the primary. For example, if schools have collapsed, the primary effect, you cannot go to school and get an education. That's the secondary. Or if water pipes have burst, the secondary effect is that people don't have water to drink, or worse, they may drink contaminated water and get things such as cholera. So we've learned about 2 earthquakes. The first earthquake we learned about was in a HIC. That was in Italy. Just put HIC on there. And the second earthquake we learned about was in Nepal, which was our contrasting earthquake, which was an LIC. And down here, I've got a list of primary and secondary effects that happened in both of them. I would recommend pausing the clip just for now to familiarise yourself with them. You don't need to remember them all, but what you do need to remember is a few of them. And the ones which I like to remember are that some patients were evacuated from hospital in Italy compared to Nepal, where actually 26 hospitals were fully destroyed. That's a good comparison. So even though it was bad in Italy, they just had to be evacuated, some people, but 26 whole hospitals collapsed in Nepal because it was an LIC and the buildings weren't as strong. Secondary effects as well. In Italy, tourism fell slightly, not much of a big deal. However, in Nepal, because tourism made up 8.9% of the country's GDP, that's the country's income, it would have had a significant long-term effect. And that was because the runway was destroyed, so therefore flights couldn't get in. How might people respond to earthquakes differently then? Well, in places like Italy, in places like Nepal, they would need to fully rebuild their hospitals and schools because they completely collapsed. Whereas in Italy, they didn't have to do that because the buildings were built to withstand that. Also in places like Nepal, due to their poorly built infrastructure and roads, they would have had to be repaired because you wouldn't be able to get food, aid and water in after the earthquake, and that could then delay response times. Whereas in Italy, they have ambulances like we have in this country, which would get to places rapidly and take care of people, anyone who had been injured during an earthquake. How are we managing and preparing for tectonic hazards then in the future? Well, we can plan and we can protect. I'm sure you can all identify here that this is an earthquake survival kit. Earthquake survival kit there. And notice what items you might include in an earthquake survival kit, such as a torch. Don't just say torch, explain why. A torch would be included in an earthquake-proof survival kit because if the electricity cut out, you can still see where you were going. Or a first aid kit. The first aid kit was included that if you were to get injured and could not access hospital, you could still take care of yourself. Protecting ourselves against earthquakes or tectonic hazards in the future might be these earthquake-proof buildings. And you might have things such as shock absorbers. Shock absorbers at the base of an earthquake-proof building, therefore absorbing the wave energy and reducing the chance of the building collapsing. You might also have automatic window shutters. Automatic window shutters which naturally come down during an earthquake, therefore the glass won't smash and fall down on people's heads. And finally there you can see the cross bracing that has been put in place. That cross bracing to reinforce the sides of the building, so if it twists and turns during the building doesn't collapse and people do not get killed in that collapsing. We're now going to move on to atmospheric hazards, including that extreme weather in the UK. To start with then, if we sketch out very quickly the shape of the Earth, I have exaggerated that purposely. And if we then had the sun all the way over here, we're going to look at why on Earth it is really, really warm at the equator. This is the equator here, 0 degrees latitude. This is the equator. And the reason why it is warmest at the equator, not because it is closest to the sun, even though that is correct, it is the closest place to the sun, but that is not why it's hottest there. It is because if we look at the amount of radiation hitting the equator, it is very, very concentrated. So we say at the equator there is a high insolation. Whereas at the North and South Pole, there is a low insolation. Radiation is still hitting it, but it is a low insolation at the North and South Pole. That just means a low concentration. And the best way then to show you is look at that surface area there, how much all of that radiation is hitting that tiny surface area. Whereas at the North Pole, that same amount of radiation is hitting a greater surface area. Therefore, more energy is having to warm up a much larger area, so each little square foot is getting less energy. That is why it is warmest at the equator, due to it having a high insolation. You can see a bit of a clearer diagram there of that the radiation, don't say sunlight, the radiation is coming in, and the surface area there is much, much smaller than the surface area at the North and South Pole. Therefore, less energy is there, and there is a higher concentration of energy there, warming it up. When we have the high insolation at the equator, that creates 3 cells. That creates the Hadley cell, the Ferrel cell, and the polar cell. Now, because we have a high insolation at the equator, that warms up the air, and that air then starts to rise. That hot air rises here, and once you've got that one in place, you can now do the rest. Follow the hot air rises, follow it round, therefore it falls there. And if you remember your swimming lanes, so if it is falling there, it also has to fall here. So you follow it round, it also then has to rise there. Swimming lanes, it also has to rise here, and then follow it round, and then it is falling there. You've now got all of your arrows in place. Now, if we know that it is rising, we know that when air rises, it cools and condenses. So here at the equator, you get lots of clouds, hence there being a rainforest at the equator. Then it is also going to be cloudy here. Therefore, where the air is falling, we are going to get sunlight at both 30 degrees north and 90. So let's get those degrees in. You've got 0 degrees there at the equator. Here you have got 30 degrees north. Here you have 60 degrees north, and then this would be 90 degrees north too. And some countries, for example, you would have Brazil there. Now take that for example. We know Brazil is very, very hot, and it is very, very rainy in Brazil, which is why we get so many trees. Whereas the next one, 30 degrees north, it is very much dry there. This is where we're getting high pressure with the air falling, and it is very sunny in Egypt with clear skies because that air is pushing the clouds out of the way. And then 60 degrees north, our example there is us, the UK. The air is rising. We get loads of rain in the UK, don't we? But it isn't as hot as Brazil due to that lower insolation. And then finally, you have Greenland and the Arctic up there at 90 degrees north. Remember, it isn't cloudy up here. It's very sunny, but it is just very, very cold too. A quick reminder, falling air is high pressure. Imagine that stick person on your desk, and if there was something coming down on top of their head, like a big, big book, they will be experiencing high pressure, which is why at Egypt and the Arctic, they experience high pressure with the air falling down on their head. Tropical storms. 2 things are needed for a tropical storm. Number 1, we need water of 27 degrees Celsius. And number 2, we need massive areas of low pressure. And how that happens then is we have water. which is 27 degrees Celsius, and that warms the air above it, and that air then starts to rise upwards. But it doesn't just rise directly up, we know it rotates as it goes up due to the Coriolis effect. As it rises, it cools and condenses into cumulonimbus clouds, and this is creating now high pressure. So that air, the high pressure now, which is heavy, is going to do two things. It's first going to sink down the center of the tropical storm. This is what we call the eye of the storm, and that is pushing all the clouds away, which is why it is very calm and dry in the eye of the storm. But also the air is going to fall down the sides of the tropical storm, and it will be sucked back in before it is rotated back up through the energy of the tropical storm. Eventually, the tropical storm will die by either going over water, which is less than 27 degrees Celsius, or going over land. There is another diagram there of a tropical storm, which, if you wish to pause the clip, you can watch that. So a very quick summary there. The water needs to be 27 degrees Celsius. The warm air rises and spins due to the Coriolis effect. It condenses and rains heavily, and the cold air sinks into the eye. They are directed by external trade winds, which directs them, and then finally they lose energy as they move over land or colder water. Do pause the clip and remind yourselves of those steps if you need to. Your example of a tropical storm is Typhoon Haiyan in 2013. Typhoon Haiyan started in the Philippines and it was very, very severe. If you can see the shape of the Philippines there, it is made up of thousands, about 3,000 islands in fact. And due to it being made of 3,000 islands, when Typhoon Haiyan actually started and went over the islands, there wasn't much land for it to lose energy. So it was only when it hit mainland Asia that it started to reduce in energy. Note on this diagram, this isn't the storm getting more intense, this is the cone of uncertainty. The tropical storm was there and they didn't know which direction it was going to go. They thought it would go in that sort of direction, in that funnel. They call it the cone of uncertainty. But as said there, the tropical storm didn't reduce in intensity going over the Philippines due to it being surrounded by water in all different locations. How can we manage tropical storms then to reduce the risk in the future? Well, we can monitor them through things like forecasting or the specially designed planes now which can fly into the tropical storm and collect data. We can protect our homes, such as putting up window shutters there or tying furniture down if it's going to be windy. And we can also plan. We can have evacuation routes, we can have storm-proof shelters, and we can have those typhoon survival kits, very similar to an earthquake survival kit. Why do we then in the UK experience extreme weather? If you look at the location of the UK, we've got a huge body of water to the left-hand side of us. We've also got a huge body of water to the south-west of us. To the east of us, then we have loads of land. So we're at this UK roundabout where we're experiencing various different air masses that can come into the UK. We've got the tropical continental air mass and tropical maritime air mass, both which is warm and wet, but also warm and dry. Then you've got cold and dry and cold and wet, which is coming in. So we experience various types of extreme weather. And there's a picture of me there drawing Beast from the East when we experience that really cold winter back in 2018 from Beast from the East, followed by these heat waves, which we also get. And it links back to the cells, which I went through previously. What we have between the polar and ferrule cell is a jet stream, which I can only describe as a wall. Imagine there being a wall there, but this wall can move. This wall here can move south to there, or it could move north. If it was to move south, that wall would disappear, and what that would mean then is that the air wouldn't rise over us, it would blow straight over us and up. We would be actually extending the polar cell, and it would flip the other way around if the wall moved north. On this diagram, you can see actually where the jet stream was. Here, you can see where that wall was. It extended just north of the UK, but then dropped significantly down. So all this green area was very, very cold weather. The warm weather was below that line there. And this is what created Beast from the East. Why did this happen? We don't know. It just did. Sometimes the jet streams like to move. So we were getting that cold polar air in from Russia, which is what brought all of this heavy snow. You can see another diagram there of that jet stream, which really went really far south. It came up a little bit and then stayed further south there. What were the effects of Beast from the East then? Well, red warnings were issued by the Met Office, which meant there was a risk to life. Thousands of people were stranded in the cars and some had to sleep there overnight. Then some shelves were left empty simply because lorries could not get to restock shelves. And then finally, some flights were cancelled or delayed too. What were the responses then to it? You can see here 5 specific responses that were put in place to Beast from the East. Do pause the clip there and familiarise yourself with that if you were to be asked the question, how did the responses reduce the effects in the future? Moving on to climate change then, the final bit of natural hazards. What evidence do we have that exists for climate change? We've got long-term evidence. These are ice cores. Ice cores are a great bit of information because what we can do is we can take an ice core like that, and once we've got the ice core, we can actually take samples at various different points, and we can sample what gas is in the ice core, which was trapped thousands and thousands of years ago. If there is lots of CO2 or different gases at one point in the ice core, we can determine what the temperature of our climate was all that time ago. But more recently, we have tree rings and we have glacial retreat. You can see from photographs, the glacial retreat is perfect evidence of climate change from thousands of years, from the last few hundred years, but then also tree rings. If I do an exaggerated diagram of a tree ring here, the closer the rings are together, that means that it was a much cooler year. But if the tree rings start to increase in size, that means that those years were much, much warmer. We can see when we chop trees now that previous years were warmer and some of them were much, much cooler. What does the evidence tell us? The evidence tells us that over the past 400,000 years, when humans didn't exist, our temperature has fluctuated. It has gone down and up, down and up, down and up, down and up. So currently we are on an upward trajectory. However, if we're looking at the causes of climate change, this may look like it is completely natural because humans didn't exist 400,000 years ago and it was only increasing then. What is the difference now? The difference now is that it is increasing at a much, much more rapid rate in the past 200 years than we have ever seen before. And this comes to the causes of climate change. We know the physical causes are sunspots, volcanic eruptions and orbital changes, whereas the human causes are deforestation, the use of fossil fuels and also agriculture there, methane. So which are more responsible? We're going to say that physical are more responsible in the long term. So that is for the past 400,000 years, specifically, orbital changes have been responsible for our climate change. However, in the past 200 years, it is human causes, specifically these 3: agriculture, the use of fossil fuels and deforestation. I'm now going to go through what the enhanced and the greenhouse and enhanced greenhouse effect is. If we take Earth a long time ago before humans existed, I'll split this into 2 sides. On this side, we have the greenhouse effect. The greenhouse effect is fantastic. We love it. Without it, humans wouldn't exist or life wouldn't exist on our planet. This side, though, is the enhanced greenhouse effect. And we know that before humans existed, there were things like cows that roamed on our planet and different animals. There was also plenty of trees on our planet that were producing oxygen and photosynthesizing, etc. Also in our atmosphere, before humans existed, we had oxygen floating around. We also had CO2 floating around. And we also had methane floating around. And what that meant is the sun also existed, and when the sun's radiation came into Earth, this is what happened. Some of that radiation was absorbed naturally by Earth, some of it came in and bounced straight back out, was reflected back into space, but some of that radiation came in, reflected back off and was absorbed by these greenhouse gases. The greenhouse gases in this example are the methane and the CO2. These gases naturally exist in our atmosphere, and what they act as are imagine tiny pillows that you put your head on at night time, pillows that are floating around our Earth's atmosphere. And what they do is they absorb heat, meaning that our atmosphere here is at a temperature that allows these trees to live, these cows and animals to live without freezing to death. It's absolutely fantastic. Without these greenhouse gases in our atmosphere, we would not be able to survive. However, humans are changing that. Humans are enhancing it. There are now fewer trees. They are being chopped down. And there are even more cows. More cows due to overpopulation. We also have cars producing CO2 and fossil fuels. So if we now look at what the gases are like, we still have oxygen in our atmosphere, but we have a lot more CO2 and a lot more methane than we did previously. So what that means is when the radiation comes down, some of it still gets absorbed, but rather than it being reflected, more and more of it is being absorbed by these greenhouse gases, meaning that the temperature of our atmosphere is no longer regulated and it is actually increasing. That is the enhanced greenhouse effect. You can see another diagram there of the natural greenhouse effect and human enhanced greenhouse effect if you wish to pause and look at it. What are the main causes of climate change then? Just to recap, we know that our Earth's temperature has fluctuated over the past 400,000 years, and it just so happens that orbital changes there happen every 100,000 years. So if you see that, 400,000, this has gone up and down 4 times. We know that physical causes are responsible for long-term climate change. However, if we look at the past 200 years, where humans have intensified their use of deforestation, fossil fuels and agriculture, the last 200 years, the main cause of climate change are humans. What are the effects of climate change? We have 4 items that I've listed here. We've got coral bleaching. That is when the radiation has become too hot for the coral and killed it. That is going to have an impact on scuba diving companies in Australia. Sea level rise in Bangladesh. People are having to be relocated. The sea temperature change influencing migration patterns of different whales. And then finally wildfires as well then in Australia. There's also a series of other effects here that I've listed, such as soil salination, actually a positive, cheaper heating bills in some countries. However, that might be more expensive air conditioning if it's going to get warmer. An increasing rate in reduction of biodiversity loss, more animals becoming extinct. An increase in tourism in some countries, and then finally increased crop yields as well in some areas, as they can now grow crops that they didn't used to. How can we manage climate change? It requires 2 things. We can mitigate against climate change, such as renewable energy resources. In this instance, we have solar panels. We then can also use afforestation, carbon capture and international agreements, all very important to reduce climate change from happening. But we also know that we need to adapt to it as well by managing our water supply, changing agricultural systems and also reducing the risk of sea level rise. What's the best way then? What do we need to do? Long term, we need to make sure that we are mitigating. For the future, for our children, their children, their children's children, we need to make sure that we are reducing our rate of CO2 and methane production through those 4 elements there. But also, we know that water supply is an issue. We know that crops can't necessarily grow today and that sea levels are rising, so we need to reduce the impact of that. So in the short term, we also must adapt.